think it's legal. Uh,
Okay, shall I start?
Maybe we start slowly. So this is. I don't think Maithreya needs a formal introduction. You all know him, except maybe. Do you know Cheshan? I mean,
Yeah, I
he's
do. I've
a
met Vishen. Yeah.
yeah.
I think we
So
have met before.
yeah, okay. We all know the speaker. We can read the subject, and so despite everything that happens in the world, math goes on, and so here's our seminar for today. So
Yeah, that's
take
right.
it away. Yeah.
Okay, great. So I'm happy to speak here. Um, yeah, I've learned a lot from the seminar in the last 3 years, and I'm glad to finally contribute back by giving a talk. So when you look at this title, the first thing which is gonna probably jump out at you, and probably you're gonna wait a second, what's going on here, is what does it mean to have a topological action of an algebra, right? Because an algebra has two operations. It has a plus and it has times, whereas hom xx has only one operation, right? And so, really speaking, the title you can claim, okay, this is a kind of a meaningless statement. But what I do mean is that many algebras, they depend on certain parameters. And what you can actually do is you can sometimes specialize these parameters so that you actually get a monoid structure and not a, you forget the additive structure, you get a monoid structure. And then you can ask the question about how this monoid acts on, well, you can ask for homomorphisms from the monoid structure to hom xx, where x is your space, right? And the only kind of, but there is one more thing one can do. It's not going to appear here, but if you have like an algebra structure, but you get multiply and you get zero.
Actually, question.
Yeah.
So if I think of a home from X as the topological space, right? So home
Yeah.
at X, it's like you can think like of a graph of that, and so
Yeah.
it would be like and then if you think about cycles in X cross X, then those you can add, right? So that's going to be
Um,
that's like an algebra.
Yeah. So if you're thinking about cycles, exactly. So the point is, that's right. So you can act on homology and cohomology, right? And so the point is that when you have a monoid action on your space, you actually get an algebra action on the homology. Is that what you're saying when you look at the cycles?
Right, I think so. So if you have cycles in X cross X, you can sort of compose them geometrically, and then you can also add them, I guess. And then they can be homology, or they can be, you can take cycles in Chow or whatever.
Right.
It depends what sort of equivalence relation you can impose on cycles, and but basically you can add them and compose them.
Right. That makes sense. Um, Yeah, in our case, in fact, like when we are basically very interested in this algebra action on homology groups. Part of the reason why I felt I was justified in writing this title is because we are really interested in many ways in how does this guy decompose as an algebra representation. Um, uh, and the point is that like somehow, like to study this as if you want to study the representations of TLN delta at delta is equal to 1, so we're looking at TLN of 1. So this is delta is equal to 1. And if you wanted to study this guy just like a monoid, I think you'll probably, you won't have a lot of fun. But studying it as an algebra is a lot easier because when you are studying the representation theory, you can heavily exploit the algebra structure to take sums and therefore construct central elements and all the good stuff that you like to do, right? So basically, when I say topological actions of an algebra, what I really mean is that the monoid acts on X and the algebras act on homology group, homology. And we're really interested in understanding the latter thing, okay? And let me motivate this a little bit. So, I mean, I don't know. in some circles and in some other circles, people may or may not be interested in topological actions. So I thought I should give two motivations for why somebody might be interested in such a thing. So motivation one is the following, is that maybe we are interested in topological, maybe we're interested in a monoid action on a group. In like the monoid action on a group. In our case, how does the Temperley-Lieb algebra at 1 act on some group? And constructing these actions on groups can sometimes be difficult, right? Because somehow the only tools you have to play with are algebraic tools, and it's hard to see sometimes whether when there's an action, how the action happens. But one way to construct an action is that suppose that that G is equal to like pi1 of X, the fundamental group of some space, and suppose I have TLN1 acts on X, then we get an induced action that TLN1 is going to act on pi1 of X is equal to G. And this method of constructing actions can sometimes be quite powerful, right? Because you are now allowed and you're able to use all the intuition and techniques from topology really to construct these kind of actions. And you will see that plenty of the arguments we'll use to construct actions on space, I mean, the arguments, well, maybe we won't see it, but we'll see partially that some of the arguments we're going to use are, I mean, they really make strong appeals to topology in many ways, and at least on a low dimensional level. And explicit how do you call it? Explicit homotopy equivalences and such things. So as a result, we can really harness our topological intuition to get this algebraic information of TLN acts on a group. And I thought I might just give an analogy for why this might be useful. I mean, which I think most people here might be already familiar with. So, for example, you have the braid group acts on the free group, right? So this is the braid free. And if you just think about this algebraically, it's not that obvious to actually construct this action. I mean, just purely algebraically. Okay, you know the braid group and generators and relations. You know the free group and generators and relations. You can say, okay, you know what? Let me try and construct this action just purely algebraically. And it's not. I mean, it requires a little bit of thought. Okay, but if you consider the braid group as the mapping class group of the n-punctured disk, and you take the free group is equal to the fundamental group of the n-punctured disk, then the action is obvious. Whereas, and you can find out, you can get the algebraic generators relation. So algebraically, not necessarily obvious. Action, not as obvious, okay? So this is my motivation number one, that maybe we're interested in actions on groups, and we can study the actions on groups via harnessing topological intuition this way. Now, the second motivation I would like to give is really coming from representation stability. Now, not that long ago, actually, like 10 years ago, basically, so people noticed a whole lot of patterns, right? So people noticed that if you look at, for example, the homology or the homology of configuration spaces, so configuration space means like of a manifold is just a collection of n distinct points of this manifold. So these are highly non-compact spaces because they're distinct points. And if one looks at the homology and cohomology of configuration spaces, one observes that these are eventually polynomial. These are eventually polynomial in N. And what I mean is, okay, dimensions are eventually polynomial in N. And people asked why. And from this was born the subject of representation stability. And secretly, what's really going on here is, of course, configuration spaces admit a natural action. These are ordered points. So configuration spaces admit an action of the symmetric group Sn. And if you consider like conf n of m altogether, so altogether, you actually can realize the H star as a stable module of the symmetric group, okay? And the way stability was defined is that you take this category, which is you have 1 point, and then you have 2 points, you have 3 points, you have 4 points, and you have, of course, all these inclusions. So you have this inclusion, you have this inclusion, you have this inclusion, and etc. And you also have a whole bunch of maps. So you have S2 acting here, S1 acting here, S3 acting here, S4 acting here, and so on. And the collection of all these maps, so basically you construct this category, which is called Fi, or this is an equivalent version of Fi. So F is for finite sets, I is for injective maps, and basically it involves, if you like, one object with one dot, or one object with one dot, one object with 2 dots, and so on. And the morphisms are given by both the symmetric group morphisms on each object, but also these natural inclusions, right? And then you say that a Fi module is an Fi module is a functor from Fi to the collection to, let's say, vector spaces. Vect K, okay. And okay, so okay, I ran out of space. Let me go to the next page. So okay, this is great. This is a symmetric group story. Okay, and okay. By the way, if somebody's interested, in case people are interested, for me, what representation stability means, for me, the way I think about representation stability is that basically these kind of finally generated Fi modules are basically direct sums of these things. So like you take your favorite symmetric group representation, maybe it's this guy, and then you start tacking on boxes to the top. So I mean, this guy includes into this guy. What is the inclusion? Well, just, you know, the basis is just the standard Young tableau. And so you're going to just put the last, okay, if this guy's n, if this guy's 5, you're going to put number 6 at the end, okay, on the top row. And so on. And let me just, okay, I know this is a little bit of a digression from the talk, but for people who haven't seen this, maybe this will be helpful for, hey, why does this Fi module kind of thing imply like polynomials in N? And you can see this directly from, if you believe me that Fi modules look like things like this, like you're just tacking on boxes on the top of a symmetric, that is, you're decomposing homology as a symmetric group representation, and the decomposition is precisely just stacking boxes on the top, then it's pretty easy to see why the dimension should be polynomial. The reason is that, for example, the character of this guy is equal to, well, the character evaluated at some tau, and let's say tau lives in this thing. What do I mean? 1, 2, 3, 4, 5. So tau lives in S5, let's say. Then the character of this thing is the character of the restriction of this thing, right, to S5. Of this thing, 2, 3, 4, and let's say from Sn, and so, okay, maybe, okay, so maybe not say Sn, let me say that this guy is n, just for ease, just for simplicity. And what? Okay, and if I'm going to decompose how this restriction is going to work, it's just going to be combinatorially going to spit out things in n, right? So you're going to get, for example, in this case, oops, yeah. So in this case, you're just going to get chi of this guy, which appears once, plus I guess n choose one, chi of whole thing evaluated, of course, at tau, n choose one, chi of uh, this guy, okay, and then plus I guess n choose two, chi of the trivial representation, okay, applied, whole thing applied at tau, and you see that, okay, these are all polynomial coefficients. So that's the connection between the how representations decompose as SN representations and how you get those polynomial conditions. So that's how the connection happens. Okay. So, but yeah,
Maybe I have two questions.
sure.
One is, how is this theory related to the old theory from like in the 70s? Lieberman has a theorem about, so he proved something along the lines that if I take a representation of some infinite symmetric group, and if
Yeah,
it's continuous in the only topology, so infinite symmetric group can, like, you can have you can think of one in the only topology, the weak or the strong or whatever, all these topologies
yeah,
are the same. And if this representation is continuous, that has this form. And then that
yes,
was later somehow generalized in many ways by Olshansky.
yes.
Is that somehow part of this theory? People
Right. So
aware of that, or?
yeah, I have seen some of these papers. My general impression when I read those papers were that this notion of stability and that notion of stability are different, fundamentally different, but they have some overlaps. I don't know that stability, the notion of stability too well, but yeah, but my general impression when I read some of those papers very briefly, I glanced at them very briefly, and my general impression is that these notions are actually different. But
Okay, but if like for example, among other things, Olshansky proves that this sort of representation they're extend canonically and not just to the group of not to the group of bijection, but like a semi-group of partial bijections, and so that's which is very, very close to that category you have on the previous slide.
I
Uh,
see.
and also the fact that the restriction, so if I have a representation and I decompose it in a smaller representation, that the
Yeah,
multiplicities are polynomial
yeah,
in the big representation. That's a general fact that has that's not
yeah,
specific to this kind of diagram. As you can ask for any kind of diagram, you can ask what's the value of the character that's going to be polynomial in that diagram. Of course, your diagram has only one, kind of one
yeah.
interesting
It has one
dimension, but
parameter.
yeah,
Yeah,
so that's why it's going to be polynomial in that variable. But in principle, it's polynomial in all of them.
sure. Maybe I mean one relation to the older work, which maybe is a little bit better, or I know a little bit better, is that so I guess Karov and Vershik have like one notion of asymptotics of symmetric group representations, and then like Bian has another group of another collection of asymptotics of symmetric group representations, and one of them is like Karov and Vershik is precisely this one, where you just attach boxes to the end and
No,
like
no, no, no. That is not. That's not that one. That one there you allowed to have multiple rows, multiple. I mean, countably many rows, countably many columns. That that is something else. In terms of representation
right,
symmetric group, that's like a. So if you think of a infinite symmetric group, it's it's a complicated group. So in
yeah,
that sense, it will have. If you ask for its unitary representation, it may have different kinds. So they can have. I mean, like the algebra of operators it might generate like all operators. It might generate like some kind of von Neumann factor and so on and so forth. And so that stuff is really you take really representation that continues in the natural topology, and then you have the von Neumann factor of type 1. And this Vershik stuff, Vershik stuff, there is a von Neumann factor of type 2, 1. or maybe you can also to infinity. But that's a different thing.
Oh, I see.
It's a different representation theory.
I see.
Yeah.
Okay. This certainly doesn't fall under the asymptotics based on Bian's asymptotics, because you're not going to get a limit shape in this case. This might be a subclass of the things that Karab and Vershik look at.
Yeah, it is the subclass around that means like it's really all this thing in Vershik Karab, they all go to the trivial representation. Because there it's only the asymptotic of the rows of colors that matter. And here you have one asymptotic equal to 1, all other 0, and that is the trivial representation.
Okay, great. So, yeah. So anyway, now why did I talk about this at all? I mean, the only reason really why I talked about it is I want to say that the reason why somehow this kind of stability works for symmetric groups is you could think about it diagrammatically. Like the symmetric group S1 is just a line. The symmetric group S2 maybe looks like things like that. S3 maybe like things like this. And right. And the point is that these inclusions of symmetric groups can be amounted to just adding strands. So the injection from Sn to Sn plus 1 is just adding a loose strand. And therefore, this is somehow leading, this is somehow a suggestive leading to say that, hey, you know what, we can maybe define representation stability for a whole host of diagrammatic algebras, okay? Because many diagrammatic algebras have the same thing, where you just add loose strands to the end, right? And because of the similarity, one can hope that there's something one can do. But then you ask the question, okay, so what is the use of representation stability of Sn? Like, as far as I can see, or as far as I appreciate, the use really is the fact that you have certain actions in nature where these stability patterns show up. So if there were no configuration spaces, for example, or the other things, but let's suppose that the only use was configuration spaces. So in that case, if there was no configuration spaces, then what would use would this abstract theory be? That is to say, topological actions and representation stability really go hand in hand, okay? And because I thought that, hey, look, maybe we can construct representation stability analogs for Temperley-Lieb algebras, I naturally thought, hey, if I want to do something like this, I better have it useful. And for it to be useful, I should study some topological actions, okay? So at least to get some kind of analog to symmetric group. So really, one of the motivations for trying to study something like this was to try and find, hey, is there like an analogous story to the symmetric group of configuration spaces and stability? Is there an analogous story from the perspective of topological actions of Temperley-Lieb algebras and representation stability? So that concludes the motivation. And now we can get into the talk proper. But before I can actually, I would like to state my results for you. But before I'm going to state my results for you, I'm going to introduce to you very, very briefly the representation theory of Tln. Tln of 1, so 1 is a root of unity. So, well, okay, 1 is a root of unity, but we're not talking about that. Like, if 1 is equal to q plus q inverse, then q is a root of unity. And as a result, the representation theory of Tln of 1 is, well, it's a non-semi-simple category. And there are some very complicated representations. There is a classification of them, but it's pretty complicated. But we won't need all of them. In fact, we only surprisingly, or not surprisingly, at least for me, I don't know, maybe I'm naive, but to me it's still surprising that whenever you have a topological action with sufficiently nice conditions, the all of your representations that occur in the decomposition of the homology turn out to be just the representations which occur in the semi-simple case, which is really nice. Now, this actually fails when I don't put such nice conditions on topological spaces. So in fact, if I do just some very, very seemingly harmless change in my topological space in the conditions that you need, this in fact fails to be true, and for a conceptually clear reason. But fortunately, we will see that that doesn't cause much difficulty, because we can always take an appropriate quotient and take the homology of that quotient. Okay, so anyway, so I'm jumping ahead of myself. Let me tell you very briefly the representation of TLN, and I'm going to talk about the semi-simple case, right? Or I can talk about n is equal to delta is equal to 1 as well. But for us, the semi-simple representations really matter, so others don't. So the idea is this, right? So we can construct a set called Mn. So this is the collection of all linked states. And what does that mean? So a linked state, so if you, for example, I think in picture is more useful than words. This is a linked state. This is a 5 to, sorry, not 5. Sorry, this is a 1, 2, 3, 4, 5, 6, 7 to linked state. Okay, and also 2 refers to the fact that there's 2 cups, and 7 refers to the fact that there's 7 strands. Okay, now great, and the point is now you can vary all your link states from 0 cups to I guess n choose to n over 2 floor cups, right? And the collection of all such linked states is Mn, and TLN naturally acts on this. How? So action is the following. I mean, it's just concatenation on the top. So for people who are familiar with this kind of thing, this will be obvious, but for people who are not familiar with this kind of thing, I thought I might as well spend a minute to tell you this, just so that, because you can follow the rest of the talk. Okay, so 1, 2, 3, 4, 5, 6, 7. This guy acts on, for example, this thing, 2, 3, 4, 5. And what is his action going to be? Well, it's going to be like this. And 1. And if I had like, I don't know, if this was something like this, then what I'm going to get is I'm going to get the same thing, but I'm going to get a circle now. And you evaluate the circle, evaluates to delta. Evaluates to delta. Okay, but in our case, delta is equal to 1. So the circle just disappears. Okay. Okay, so that's what the Mn, the collection of all linked states, is. And this, we saw that this guy has a natural action of TLN, and Mn has a natural filtration on it. So Mn has a natural filtration which TLN action respects. Namely that, namely that you look at, let's say, I don't know, WNP to be the collection of all linked states, let's say span of all linked states with greater than or equal to P cups. And then, and notice that the point is that if you act by an element of TLN on a linked state, you can only increase the number of cups. You can never decrease the number of cups. So because you can only increase the number of cups, and because you have a greater than or equal to condition here, WNP is TLN stable. And you can consider, so whenever you have this kind of filtration, right? You have a filtration, you have a, let's say Wn1 is bigger than or equal to Wn0 is bigger than or equal to this guy's Mn. Dot, 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 Wn, sorry, Wn, I guess n by 2 floor. Whenever you have this kind of a filtration, we can take quotients. And so you define VNP to be the quotient of WNP by WN P plus 1, I guess. And this guy is called your standard representation. Rep of NP link states. Now, when delta is semi-simple, VNP is irreducible, and in fact, all of the irreducible representations are just VNPs. Okay. When delta is not, when you're not in a semi-simple case, there are other representations. But when we put nice conditions in our topological space, the only representations which will occur for us are the VNPs. So that's great. So this is literally, well, there'll be some construction about the structure, like appeal to the structure theory that goes into the study representation theory of TLN later on. But as representations, this is the only thing from the representation theory of TLN that one really needs to know. Okay, apart from that structural feature. So
and maybe also the definition. Like
what?
for example, I'm not sure. I've maybe you should remind us the definition. Like the crossings are not allowed in this algebra, are they? Or like when you
oh, right. So I'll
the
define
actual definition of the algebra you consider. Maybe you could remind us.
Sorry about that. I will define TLN. Well, you can understand the Temperley-Lieb algebra representation theory abstractly for now, or you can understand it concretely for now. And I will now tell you the generators and relations of the algebra and how to think about them, okay? I think, Andre, it was you who said we should not think about an algebra by generators and relations. We could think about it. We should think about them in terms of representation theory.
No, it's fine. It's fine to think about them with pictures, but it's good to be also specific as to what pictures they allow.
Of course, I'm making a joke. Of course. So let me do that. And actually, there's a method to the madness. The reason why I postpone the generators and relations is because by looking at those generators and relations, we will then directly get our first foot into the door to find some elementary properties about topological actions. So we can do those together, and let's do them right now. Okay, so I'm going to specialize to I don't need to specialize to delta is equal to 1 immediately. But okay, so here are what the relations are. So TLN, okay, by the way, the definition in one line, TLN is the collection of all crossingless pairings, okay, from n dots to n dots. So that's what the definition is, okay? But in terms of generators and relations, you can define UI to be this guy, where this is the ith strand, this is the I plus 1 strand, and there's ones everywhere else. There's just lines everywhere else. And the generators and relations are the following, that UI square is equal to delta UI. So for us, delta is 1, so UI square is equal to UI, which is very nice because that means it's an idempotent. Hint, hint. Okay. The second relation is that UI plus 1, UI is going to be equal to UI. And the third relation is going to be that UI uj is equal to uj UI for I minus j bigger than or equal to 2. Now, the third relation basically just says that if I have 1 cup and one cup looking like this, and I have another cup looking like this, I can slide things up and down. Okay, so that's pretty clear. For the second one, let me just draw the pictures for you, in case you're like, sure. The picture is this, so this is for 2. The picture is that ui plus 1, ui. Okay, and you just draw this. Hey, and then you straighten out that line, and you get something like this, which is just ui. Okay. So these are the generators and relations. Okay, and now, so right, so hopefully we're now enthusiastic to study topological actions, and now we understand what the representation theory looks like. So now the first step, like the naive way one would go about doing this is just, okay, we have generators and relations. Let's find out what these topologically mean. Okay. Now, firstly, what are the idempotents in hom XX? So hom XX idempotents are just retractions. So I'm going to call this the idempotent relation, and one says that each ui x, and let's call it the retract ai, is a retraction. It's a retraction. What does the second one tell you? It tells you that, well, ui plus 1 ui, let's see what happens. So x goes to ai, then it goes to ai plus 1, then it goes back to ai, and this is equal to just the map x goes to ai. And what that really means is that this map, this composition, must be the identity. Oops, this composition must be the identity map. That is, so this is the first one. Oh, sorry, what am I trying to do? Let me use a different color. This is the first relation topologically. The second one is basically going to say that ui restriction ai plus 1 is an isomorphism from ai to ai plus 1. Oh, sorry, ai plus 1 to ai is an isomorphism with inverse ui plus 1 restriction to ai. So basically, what it's saying is that not only, so we saw that not only we have retractions, but in fact, all of these retractions are isomorphic. And how are they isomorphic? They're isomorphic just using these UIs, right? So just by moving these, just by applying UI plus 1 on AI, you get an isomorphism to AI plus 1. Okay. And the third thing, which elementarily just we see, is basically that, well, think about it. So if you have a commuting family of retractions, what does it mean? It means that, so if you take X and uj of X is going to live in AI, ui of X is going to live in EJ. So the fact that these guys commute means that uj and ui are actually retractions to AI intersection AJ. And what that actually means, and it fixes everything in AI intersection AJ, right? So what that actually means is that UI restriction to AJ is going to be a retraction to AI intersection AJ. Okay. So let me just write that. I just explained it in words because I ran out of space, but you can feel free to ask me if it was not clear. UI restriction AJ is a retraction to AI intersection AJ. So, okay. So that is when I and j are bigger than or equal to 2, right? So I just need this condition. Okay? So these are the 3 relations, and those of the Temperley-Lieb algebra, and now we've written down in terms of generators relations, And these are the three topological things they translate to. So finding a topological action is essentially finding some kind of retraction pattern which satisfies in this specific kind of pattern. So it satisfies these conditions, but it's some kind of pattern of retraction. So that's how we should think about it. Okay. Okay. So now I'm gonna go ahead and state the results. And they're quite nice, if I might say so myself. Maybe I shouldn't. But okay. So let Q be the fixed set, that is the fixed set of X. This fixed point subspace of X. Then for X sufficiently nice, so theorem, HK, okay. First of all, okay, so maybe I have to slow down a little bit. So, okay, associated with X, we will define a very natural auxiliary object, which is a filtration of retractions, okay? We will define a filtration, an intrinsic filtration of an auxiliary object, which is a filtration of retractions. So I'm going to, this guy, which is X, which contains of R1, contains R2, all the way goes to Rn/2, and that contains Q. So it's some filtration of retractions. And actually, explicitly what it is this guy, the spoiler is that this guy's A1, this guy's like A1 intersection A3, and so on. And the point is that this kind of, all of these filtrations are going to be the same. It doesn't, indices don't matter. We'll show the indices don't matter. So this filtration is really an intrinsic object because the indices don't matter. But you can think about it as A1 intersection A3. So recall that the AIs were just the retractions which the UIs go to. So the UIs retract to AIs, and you're looking at this intersection pattern of retractions. And this is the filtration associated with that. Okay. And for X sufficiently nice, we have theorem. Let's say HK of X is equal to the direct sum of, I guess, P is equal to 0 to n/2 floor of V and P. So these are the representations you saw earlier to the exponents. And let me call the exponents SP, and I'll give you a formula for it, where SP, and it's a very nice formula, is going to be, well, let's see, the sum for all Q. So okay, first I need okay. So it's dim of RP. So RP is the element of your filtration, plus sum for all Q bigger than P, minus 1 Q, minus 1 to the roll down, sum over all Q bigger than P, sum over all lambda in comp Q minus P. So comp is the compositions. It's the number of unordered ways to sum to a given number. Number of ordered ways to sum to a given number. Minus 1 to the row lambda times D, well, let's say RP lambda these are combinatorial coefficients which you know explicitly, but they also are defined recursively, just like symmetric polynomials are. So they're quite nice. So, and then times dim of R cubed. Okay. So, okay, so what's going on here? Just the key things which I want you to take away from this kind of formula is the following, okay? Firstly, only the VNPs appear. Okay, so I should also do one caveat. I have to take x mod q. The reason is otherwise that statement is false. Okay, so only, and you can construct explicit counterexamples. So the first observation is only VNPs appear. And this is a priori reasonably surprising, because it's surprising because there are so many representations when delta is equal to 1 other than the VNPs, but none of them appear. And moreover, those representations, the less pretty ones, appear even when you don't consider x mod q. So if you don't quotient out by q and you have a non-trivial full intersection, so if you fix points, if you like, then in fact, you do not actually have this condition that only the VNPs appear. The second thing which I want you to take away from it is you can read it off explicitly from its filtration. And to me, that's surprising, because the filtration is something you know very explicitly. It's very explicit. And the fact that, hey, look, you have the filtration. For example, the filtration could be like the torus contains the circle, contains star, 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 okay? This contains a single point, okay? And then the rest is a single point. So that could be your filtration. And just by knowing the filtration, it means that you know the entire representation structure of the homology. To me, that's surprising. And the third feature of this is that it has this very nice combinatorial form. And the reason why this combinatorial form comes in, as we'll see later on, is it's because of an inclusion-exclusion type of argument, okay, that this is really coming about. And I think we'll see it by and by. When we get to the theorem, if we get to that, which I see some time has already gone by, but we'll see. So if we get there, we'll see explicitly why you get this formula exactly how it is, and I will try and get there. So, yeah, is there a question? I heard.
Yeah, sorry, somebody else has a question? So what's sufficiently nice is, I don't have to give specific, but it's
right.
You mean like a CW complex or what?
Exactly.
Or some...
So I need X to be a finite CW complex with each retraction is finite. So that's what sufficiently nice means. And I also need the action to be surjective, which means that I need like TLN should move every part of X, or like, I guess what I'm trying to say is X should be the union of the AIs. There shouldn't be some point of like, there shouldn't be some extraneous part of X which is not inside the AI. So that's one condition. And the second condition is, of course, that F is a finite CW complex, and with each of the AI should be also a finite CW complex. Now, you may ask, wait, why do you need the condition that the retractions are also a finite CW complex? Is that not already, can that not be derived? In fact, I mean, but you won't ask that question because I know that you guys know this stuff really well. There is a K-theoretic abstraction called Walt's finiteness criterion, right? And Walt's finiteness criterion will basically say that if you have a retraction of a space, that retract does not necessarily, and if the space is a finite CW complex, the retract does not necessarily have the structure of a finite CW complex. And it will have the structure of a finite CW complex if and only if this particular K-theoretic class is 0. So therefore, I need that additional hypothesis. So So X is a finite CW complex. All the AIs are finite CW complex. and X is the union of the AIs. So those are the conditions. So that's what sufficiently nice means. Okay. Okay, so I thought that rather than maybe I should state the second theorem, and then I'll give you examples. Then I thought that rather than, I would give proofs and as much as possible, give you the ideas of various proofs, but I would also, without examples, you don't know what you're looking at. So I should give you examples of topological axioms in TLN, but before I do that, I'll give you some baby examples. But before I give you some baby examples, I want to state the second theorem, because if I spend some time on motivating it by representation stability, I should at least tell you the theorem which relates to representation stability. So theorem is that, so remark, I would say that in the notion of stability that I define, so I define a particular notion of stability of TLN for TLN representations, and in the notion of stability which I define, which is very analogous to this construction as like a functor from Fi. So I define a category called LS, and I consider functors from LS, and that's the notion of stability I defined. And the remark is that the VNP, so if I take V, let's say 2PP, which is contained in V 2P plus 1P, etc. And what I will denote this by V and P, right? This guy is a stable object in my category. Okay. And the theorem is the following. And the theorem can be essentially just read off from the previous theorem. So maybe this is really a corollary. Is that if I define a notion called P filtration stable, and the point is that filtration, so you have to ask, like, what does topological stability mean? So in the case of symmetric groups, like configuration spaces, like they really seem like a topologically stable thing. Like, so what does topological stability even mean in this context? You need to define something like that, right? And for us, we have this beautiful auxiliary object, which is our filtration. And the filtration has a natural notion of stability, namely it stabilizes. It's constant after a particular point. And so we can define topological stability to be the filtration stability, right? So I call a collection of spaces, I have a notion of P filtration stability of topological spaces, and the theorem says that if, let's say, Yn or Xn is a P filtration stable sequence of spaces, then Hi of Xn modulo, this is a growth in D quotient. So I'll tell you what that means. I guess I need to Vn0 up to Vn t minus 1. What that means is that I essentially set, if you like, I remove all the terms which are Vn0 to Vn t minus 1. So that's what the quotient means. Is representation stable. And this can be read off directly from the previous theorem. The reason is because, the reason is because if you look at the sum only depends on Q bigger than P. So if I kill away the, so you have a collection of V and P's, and the sum only depends on Q bigger than P. And here I'm basically, I'm killing the small guys. And so if filtration stable means that it stabilizes after P. It stabilizes, what am I trying to say? Yeah, it's P filtration stable means it stabilizes after P. and the sum is the sum of Q bigger than P, and therefore the corollary can be read out from the theorem. So I've not told you what many of these things mean in precise terms, but I don't think it's entirely very important. I think you get, the main thing I want to communicate is that there is an analogous theorem of the fact that configuration spaces are like the homology of configuration spaces are representation stable. Basically, we have an analogous theorem here where the homology of natural families of stable spaces are representation stable. So that's basically the philosophy. It's more a philosophical statement than a, I think the use is very philosophical in nature than mathematical in nature. Because in this case, you can deduce the structure explicitly. By the way, if you ask you ask anybody you want, explicitly tell me what irreducible representations of the symmetric group occur in the homology of your favorite configuration space of your favorite manifold, people won't be able to tell you. These are open problems. I mean, these are hard things. Even for RD, like even for the real like Euclidean space, you have some kind of some characterization of how the homology looks. But if you still ask somebody, like, what are the irreducible representations of Sn which occur in this decomposition? I think, well, feel free to prove me wrong, but as to the best of my knowledge, people won't be able to tell you that. And so in that sense, this really differs in flavor from the standpoint that here we actually know the decomposition explicitly. There we don't really know the decomposition and it's open. So it differs from this standpoint, but the same kind of philosophy that a stable sequence of spaces gives a stable sequence of representations, that philosophy is preserved. Okay. Okay. So now that we've stated our theorem, let me give you some examples. Examples are always good. So the first example is going to be, take your two-sphere. Okay, if you like. I mean, you can generalize this example. It's very easy. Basically, you take two spaces and you connect them somehow. So here, you have two things. You take A1 to be the upper hemisphere, A2 to be the lower hemisphere. You have a map U1 going this way, and you have a map U2 going this way. And how this map is, these maps are essentially fixing the intersection. So it's like bobbing it's like taking it's fixing the circle in the middle and it's just taking the hemispheres to each other. And this is an action of TL3. 3. So recall that TL3 is generated by U1 and U2, right? And U1, the only relation we really need to check is that U1, U2, U1 is U1, U2, U1 is U1, okay? But we already translated this into topological languages. All we need to check is that U1 is an isomorphism from U2 to U1, and U2 is an isomorphism from U1 to U2, and they fix the intersection. And that's precisely what happens here. So you have these kind of easy actions, baby actions of TL3. Okay, what's this? Another example. So also, I'm going to call it the cheating example. So cheating example is the following: like take VNP, take link states, add a loop for every link state, and act by action on link states, and if you get 0, then send to the center point, send to the wedge of these loops. Okay, so send to star. And so what this means is that, like, you're really looking at spaces like this, and these could be various link states. So for example, if we're going to do like, I don't know, TL5, and we're going to consider V5 too, then what are our possible links? Link states. We can have this guy, we can have this guy, we can have this guy, and then we can have this guy, and then we can have this guy. Okay, so each loop corresponds to one link state, and you just act on it by action on link states. Okay. In this particular case, nothing ever goes to 0, but for other cases, things can go to 0. So if we did the V5-1, things can go to 0, and if things go to 0, then you just send it to the center point. And otherwise, you just act by the isomorphisms of taking loops to each other. So this is an action, well-defined action, just it's a cheating way. It's a cheating example. I call it the cheating example because it's cheating. It's basically saying that, hey, look, this is a good well-defined representation. I'm just working backwards to construct a topological space. Okay. Let's do a baby but interesting example. Okay, so I've given you one super baby example. I've given you one cheating example. You're entitled to a baby but slightly interesting example. And maybe if we get through the end, I've actually written a not so baby an interesting example. So we'll see if we get there. But for now, we have a baby but slightly interesting example. So this is going to be a TL4 action. And what I'm going to do is the following. I have a torus, so this is T2. I have another torus, this is T2. And I have a third torus, okay? And the UIs are going to be retractions onto the AIs. And this guy is going to be A2. This guy is going to be A1. This guy is going to be A3, okay? And the action is the following. So let me color code it. So the U2 action, so this is going to be U2. So remember what U2 must do. U2 is adjacent to both 1 and 3. So U2 must be an isomorphism from both 1 and 3 to U2, to A2. And so U2 is just an isomorphism over here. And what is U1? Well, U1, it must be an isomorphism from U2, but U3, it should be a retraction. Now, the common thing that these two toruses have in circle, this is a copy of S1. And so U1 is going to retract this torus T2 into S1. And it's going to take this guy isomorphically. Okay. And U3 similarly is going to retract the A1 torus to A3, and it's going to take A2 isomorphically. Okay. So this is a well-defined, one can check that this is a well-defined action of TL4. So it satisfies, so basically we've constructed it so that, remember what the criteria were, right? So let me just go in order. 1, each UI must be a retraction. They are. Okay. 2, how do you say? I plus 1, UI must equal to UI, and topologically, what this means is that UI and UI plus 1 are isomorphisms from AI and I plus 1 to each other, and are mutual inverses. And we've arranged it so in our case, I plus like one of them has to be A2, and we've arranged it so that A1 and A2 tend to each other isomorphically, and similar A2 and A3 do the same. The third criterion we needed was that UI uj is equal to uj ui for I minus j bigger than or equal to 2, and in this case A1 and A3, and what topologically what that meant is that the A3, like U3 restriction A1 is the retraction onto its intersection, and U1 restriction A3 is a retraction onto its intersection. And indeed, we have U1 and U3 to be retractions from A1 and A3 onto the circle. Okay, so this is what this example, and I think it's reasonably interesting. It's generalizations of this thing. You can generalize it, and you can get a stable sequence of spaces like this. So in this case, the filtration, right? Well, this is X containing what? T2 containing S1 containing star. This is what our filtration looks like. Okay, this is the well, yeah, so this is the full intersection. This is the double intersections. This is the double intersection for far away things. Remember, neighbor, okay, we don't know neighbors yet. So this is double intersections. And this is the AIs. And if I just write the filtration over here, so in this case, the filtration is going to be, of course, X, but this contains, I guess, S1, it contains star. Okay. So this is how the filtration is going to look like. How do I say? So in this case, you have multiple, you have a possible for triple intersection. Do you? Yeah, because you can take A1, A3, A5, but that's also star. So notice that you have double star there. That's what I meant by filtration stabilizing. So in this case, filtration, you notice it stabilizes after, I guess, position 1. Okay. And in fact, yeah, so the as a representation, yeah, so it's going to stabilize after position 1. So what that means is that the Vn2 term is stable, and so in fact you're going to get V52 here as the representation structure, and that's obvious because we just cheated and we constructed it backwards. And over here, the filtration is well, X of course, but this is contained in each one is like a disk, and S1, right? And X was S2. Okay. Okay. So now I've given you some examples. I was originally planning to, I guess, walk you through this a little bit slowly, but maybe I have to state some things so that we can actually get to the interesting stuff. I mean, there are, like, the first part is, I mean, quite a decent amount of elementary stuff. The second part is the topological stuff. And the third part is where the structure theory of the representation theory really comes into play. And I think 2 and 3 are quite interesting. 1 is also interesting in its own right, but maybe 2 and 3 are a bit more interesting. So let me try and get there. But yeah, to even motivate some things in 2, you unfortunately need 1. So, okay, let me just state what it is, okay? So, a fact is the following, is that, so look, the way you should think about it, so a TLN action in a space is some kind of retraction pattern. We saw that far away intersections play an important role. That is A1 intersection A3, A1 intersection A5, A2 far away intersections play an important role. Neighborhood intersections is something we've not quite touched upon yet, and you might ask why? Why have we not touched upon it? So the fact is the following, is that in fact the neighborhood intersection is equal to the full intersection. Is equal to full intersection. And if you remember, we call this Q, the fixed set. Because in the full intersection, everything is fixed, right? Yeah. So the neighborhood intersection, the reason why, so, right, that is your X lives in AI intersection AI plus 1 implies that actually X lives in everything. A1 intersection A2 intersection dot 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 intersection AN minus 1, and this is just Q. And the way to prove this is by a trick, by like an algebraic trick, like you're considering a particular map and you compute things in 2 different ways and then you get it. And I'm going to skip it. Proof is an algebraic trick. Okay. And okay, so fact 2, which is I think you guys already probably understood already. Fact 2 is that the isomorphism class of AI1 intersection dot 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 intersection AID depends only on D, i.e. on the cardinality. And this is just because the UIs are isomorphism. So for example, I'll just do an example. It's very easy to see. Let's say A1 intersection A5 goes via isomorphism to A1 intersection A6 via, I guess, U6. And that goes to an isomorphism to A2 intersection A6, if you like, U2, and so on, etc. So, and remark is that this is what makes our filtration intrinsic. So this filtration with this auxiliary object we constructed, which plays an enormous role in it, it's so important. Not only in the statement of the main theorem, which decomposes homology group, but also to define stability. If there's a single most important definition, it is this filtration, which is the auxiliary construction to the action on our space. Okay. And of course, I already said in words earlier what the technical conditions are, and so I don't need to go into that. That surjective action, so it means to be the union of the AIs, and the finiteness conditions, right? Okay, so then you have some. I think in order to give you the idea behind how the main theorem is proved, which is actually what my goal for the remaining 15 minutes is going to be, I have no choice but to introduce to you a particular topological lemma and its corollary, and we'll do that. And this is where most of the topology is concentrated. Okay, and it basically, but the statement is very believable. Okay, the statement is that if alpha lives in, so this is the homological version of NIFI. Okay, NIFI means neighborhood intersection is equal to full intersection. Okay, so if alpha lives in, okay, so okay, I need to say a little bit in words. Okay, now since each AI is a retraction, the point is that AI, including to X, induces an injection from the homology, right? Because there's a special property of retractions. So then I can really talk about homology classes of X actually living in homology classes of my retractions, okay? So if alpha lives in HK of AI and alpha also lives in HK of AI plus 1, then alpha lives in HK of, sorry, what am I trying to say? Yeah, then alpha lives in I star HKQ. So Q need not be a retraction. Therefore, I need the I star HK of Q. Q is the full intersection. And let me give a counter example that this is false for non-surjective actions. Counter example for so this is where we use surjectivity, that X is actually the union of the AI. So surjectivity is something we can't really do away with. I mean, it's not just for convenience that we do it. You actually need it. Counter example for non-surjectivity. You take a cylinder. I can take this guy to be 1, so that I can take this to be A1. Sorry, I should have, okay, I'm going to take this to be A2. And like TL3 acts on this guy, right? A1, A2. Okay, but so this TL3 acts on the cylinder, but not surjectively. And because the action is not surjective, notice that A1 and A2 are, notice that A1 and A2 are homotopic to each other. So homologically, they're the same class. So alpha here lives in AI, it lives in AI plus 1. But notice that Q is equal to star. So alpha does not live in I star HKQ. This is a counterexample for non-surjectivity. So you really need this surjectivity. But this is believable if you believe NIFI. So if you believe that neighborhood intersection is full intersection, then this is actually very believable. Though actually it's not at all easy to prove. It actually takes hard work to prove this thing. So most of the topological work goes into proving this thing. Okay? And in fact, a corollary of this, and this is something which I want to prove to you, because the proof is not hard, but I want to somehow drive the idea home, because this is somehow the most important idea behind how to prove this main theorem. The corollary of this is that minimal intersections are unique. And what does that mean? Okay. It means that, like, if alpha lives in HK, so suppose that it lives in two intersections. So AI1 intersection dot 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 intersection AIC, and also lives in HK of AI1 intersection dot 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 intersection AID, where both of these are minimal, both minimal, with respect to inclusions, then in fact these are equal. Then I1 IK is equal to J1 dot JK. Okay. And the proof of this is using the previous lemma. So if there exists some J, so case 1, if there exists some J with J minus I is bigger than or equal to 2 for all I, then applying, since uj of alpha is equal to alpha, we can apply uj into the first guy as well, and that's going to be retract. So uj of alpha is equal to alpha is because of this thing, and then implies that alpha lives in HK of AI1 intersection AIK, AIC, I think I called it, intersection AJ, and so contradicts minimality. And that's because of this thing. And case 2 is the case which follows via our lemma. Because if otherwise, alpha lives in HK of AI and it also lives in HK of AI plus 1. Alpha lives in HK of AI and alpha lives in HK of AI plus 1, implies that alpha is actually in I star HKQ. As a homology class. And what that means is that the minimal intersection is Q, because Q is the minimal of everything. It's the full intersection. It's intersecting everything. So it implies that minimal intersection is Q. Okay. So now that we're convinced that these minimal intersections really do work, this is somehow the key idea we need to prove the theorem. And the key, so the theorem, which is the immediate precursor to our theorem. So modulo the combinatorics in the end. The theorem which does all the work is the following, which is immediate precursor. Is the following. Is that if, yeah, so if alpha is an HKX has minimal intersection, how do you say, A1 intersection dot 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 intersection, let me say A1 intersection A3 dot 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 intersection A2 P minus 1. So this is P terms. And by the way, this guy was our RP. And also has the property that A dot alpha lives in a further intersection implies that A dot alpha is equal to 0. That is, it's a further property that if you live in, if you have, so this element of, so A is an element of TLN. If you act by some element of TLN and it sends it to something further, then you better set it to 0, so you better kill the class. Then the cyclic module, TLN module, generated by alpha, is VNP. Okay. And where is the P coming from? Like, what is this P? This P is the same as this P, which is, okay. So it's coming from the minimal intersection. And the proof is the following map. I won't have time to present to you the proof. I would have liked to. But the proof is, because it is a very nice proof, at least I think so. So the proof is, we construct the map from VNP to TLN.alpha by sending this guy to alpha. Okay, so let me pause here because this is a very, very important observation. So the point here is that the way to translate, so this is the key statement in this entire lecture, okay? The way to translate between the algebraic language and the topological language are through minimal intersections, okay? Minimal intersections are well defined by the topological lemma. Now, algebraically, the minimal intersection is basically where the length 1 cups are. So in this case, notice in this diagram I've drawn, my length 1 cups are at position 1, 3, 5, dot, 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 dot to 2p minus 1. And notice that if I act ui on this link state for I less than p minus 1, for I is equal to 1, 3, 5, etc., not I less than p, okay, not I less than p minus 1. What I meant is, if you act ui on this die for I is equal to 1, 3, 5, dot, 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 up to 2p minus 1, then it just preserves it. Because you're just going to get a circle, and that's going to get evaluated to delta, and delta is 1. On the topological side, if I act, since alpha lives in A1 intersection A3 dot dot A2p minus 1, if I act on alpha by each one of those U1, U3, U5, etc., again, it's going to stabilize alpha. Alpha is going to be preserved. So the minimal intersection on the topological side, we've defined it already. And on the algebraic side, it really means the position of the length 1 cups. So let me just do an example. So let me do, for example, the minimal intersection of this thing, right? So this is some, right? This is some link state. And just look at it. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Well, look where the length 1 cups are. You have a length 1 cup here, you have a length 1 cup here, and you have a length 1 cup here. So it implies the minimal intersection is going to be A2 intersection A5 intersection A10. That's all there is to it. Okay. So let me just say a few words about how we go from this theorem and we get the main theorem. Okay, so what the content which is remaining is how the main theorem, how this theorem that we wrote down can be used to, along with a little bit of combinatorics, to give you the final theorem that you desire. And the way is the following: is that right? So the point is that if you take some, supposing I have some alpha, and let's say this alpha has a very large minimal intersection. Okay. Now the point is, in the Tln.alpha, I can get my smaller minimal intersection as well. Okay, so for example, if I do something like this, so this is 5, and then I do, I don't know, something like this. If alpha is equal to the image, if let me call it beta, H. So let me call that map H, by the way, so just for ease. So let me call this map H. Okay. So if alpha is H of this thing, right? If beta is H of this thing, then notice that notice that beta lives in HK of A1 intersection A3 intersection A5. Okay, maybe I'll just add 3 of them. Okay, no, you know what? Let me not do that. Intersection A7, intersection A9. So it lives inside this intersection, but this is not the minimal intersection of beta. And what that really means is that things in further minimal intersections contribute even terms to so things in further minimal intersections contribute some terms to things in the larger minimal intersections. Okay, and what that means is that, so if you recall, right in the beginning we had this. Okay, let me scroll to the top. Oops, yeah. So right at the beginning, we had this thing called SP. Yeah, we had SP. This term is the term which comes from your P minimal intersections, that is A1 intersection A3 intersection A5 dot 2P minus 1. These guys come from further minimal intersections. And how many of them are there? Like, how many link states do I have in a given intersection from a further thing? And you can describe this easily by the following. So it's just going to be, so I take, in our case, we have 5 things. And in the remaining, if I'm looking at Q bigger than P, then I have n minus 2p, I have n minus 2p strands, and I have q minus p cups that I need to fit in there, and I can fit those cups anywhere I want. And so actually what I'm going to have is the number is going to be the number of link states with n minus 2p strands and q minus p cups. So the number of link states with n minus 2p strands and Q minus P cups is just dimension of V n minus 2P Q minus P, and you call that dimension, I define it to be D n minus 2. So I defined it to be, D, fine, it's Dn minus 2P Q minus P. And in my notation of the D lambdas, this is going to be D lambda RP, where RP is equal to n minus 2P. Okay? And yeah, so I'm a little bit over time. Now, I would ideally like to just compute maybe one tiny example for how the combinatorics actually works to compute these dimensions, and I think that would actually make things very clear. But because right now it might be a little bit abstract, but I'm gonna end it now, and if people are interested, they can ask me that as a question.
Great. So questions. Okay, maybe I'll go first. So in your definition, you there was obviously like the Dynkin diagram of type A, right? Can you, it's presumably you can define like Temperley-Lieb type algebra for like an arbitrary graph? Does that make sense?
So what you're saying is that in the definition of a Temperley-Lieb algebra itself, you're looking at crossingless matchings, and you can think about it as crossingless matchings of a graph of type A to itself. So Andre, I think one of the problems you're going to run into there is, you're in 3 dimensions now, and you can kind of wiggle things around. But let's say you're even restricted to move in 2 dimensions. So let's say you even take a graph and you consider that like a 2-dimensional projection of the graph in 3-dimensional space. Then, and let's look at that singular point. So let's try and think. I'm just thinking aloud here at the moment. You look at that singular point, and you're looking at crossingless matchings. How do they behave around that singular point? Well, yeah, I could consider things like that and like that. So I guess, yeah, so there is some ambiguity, Andre, right? Like, because
no, I guess what I meant is that you have some operators, they you have 2 kinds of relations. Some their projectors commute, and some of them not exactly commute, but that's some kind of like, feels like a graph, right? So you could, well my actual question is that, is there can you like people study like group generated by reflections. Is there meaningful discussion of like group generated by retractions, or some such things?
That's a good question. So what Misha said is that retractions are very hard. That was his answer to the problem, and that trying to understand all retractions of a topological space is somehow, in his opinion, was intractable problem. Or that was the impression I got.
No, I meant is if you're interested in like groups generated by reflections, okay, that's a beautiful theory.
Yeah.
But of course you can
Ah.
while of course if one single reflection or one single retraction, okay, maybe we don't understand them so well. But if asking for like a finite group generated by them,
That's a very interesting question, actually. Yeah, so given a space, what are some kind of, maybe we can't understand everything, but maybe we can find some kind of algebraic properties of the group generated by retractions in our space. And maybe they'll have some nice structure theory. Yeah, I've not actually thought about that in that. Yeah, I've not actually thought about that. That's a very interesting question. Yeah. And maybe these collection of retractions that we got with these particular relations have formed like a natural submonoid of that larger group, and maybe there's a nice characterization, and maybe so it'd be very interesting to study algebraic properties of or structure theory of such a group. Yeah, I agree.
All right, that sounds like a question for the future. How about more questions for right now? Is that anybody has a question? Well, well, I guess I asked enough questions for everybody during the talk.
Yeah.
Maybe
Thank you.
well, let's thank Maithreya and wish everybody a happy election day, and meet again next Tuesday. And thanks so much.
Thank you.